Dear students, continues to the applications of an operation amplifier. In the last session, we discussed about the three applications of the operation amplifier. One is how Opamp can be used as an inverting amplifier, and the second one is how Opamp can be used as a non-inverting amplifier, and third is how Opamp can be used as an inverting adder. So these three applications you studied in the last session, and you also studied how to derive the expression, then the waveforms. In this session, you are going to learn about the remaining applications like voltage follower, next integrator, and how Opamp can be used as a differentiator. So let's start with the voltage follower. So dear students, you are observing the diagram of an voltage follower and also the waveforms. See, by seeing the figure and the waveforms, it is understood that in this application, the output voltage which follows the input voltage. So the circuit which performs this operation is called voltage follower. So voltage follower is one of the applications of the operation amplifier. So where the output voltage follows the input voltage. See, from the circuit, what is the potential at the node B? So in this case, the voltage is applied at non-inverting terminal, so that the potential at the node B is V in. Since using the virtual ground concept, the potential at node A is also equal to potential at node B, which is nothing but V in. Then, since node A is directly connected to the output, you are observing node A is directly connected to the output. So which means that V0 is equal to VA, means output follows the voltage applied, voltage at the terminal A. So as we know, voltage terminal A is equal to Vin according to virtual ground concept. Therefore V0 is equal to Vin. Since V0 is equal to Vin, what is the gain? So the gain of this voltage follower is unity. So such a voltage follower is also called as emitter follower or source follower or unit gain amplifier, buffer amplifier, which is also called as isolation amplifier. So next application we'll see. So I hope you all understood. So how the Opamp can be used as an voltage follower. So in the waveforms also you are observing that. So output, the waveform of the output voltage which follows the waveform of the input voltage, since V0 is equal to Vin. So next application is that integrator. So how the Opamp can be used as an integrator. So this is also, once again, all the applications are very, very important for examination point of view. Guys, please refer the circuit diagram and try to derive the expression, output expressions or gain of the various applications of the operation amplifier, and also the problems. Concentrate the problems on these applications. Integrator. In an integrator circuit, the output is the integration of the input voltage. The figure shows an integrator circuit using an Opamp. From the circuit potential at node B, VB is equal to 0. Then use the virtual ground concept, since then the two terminals, input terminals are the same potential. So which means VB is equal to 0 means VA is also equal to 0. Then find out the current which is flowing through the resistor, or then apply KVL to this. You will get I is equal to V in minus VA by RF, or I1 is equal to V in by R1. Next, what is the current flowing through the capacitor? So IF is equal to CF into dV by dt. Since then V is nothing but VA minus V0 here, then IF becomes CF into d of VA minus V0 by dt, and VA is equal to 0 according to virtual ground concept. You can write IF is equal to CF into d of 0 minus V0 by dt, nothing but IF is equal to minus CF into dV0 by dt. And since the operation amplifier, this operation amplifier input current is 0, I1 passes through RF as IF, that is I1 is equal to IF, which means IV in by R1 is equal to minus CF into dV0 by dt. Then dV0 by dt is equal to minus V divided by R1 into CF. See, integrating both sides with respect to t. If you integrate both sides of the equation, so what you will get, integration of dV0 by dt into dt is equal to minus 1 by R1 into CF into integration of V into dt. So where integration of dV0 by dt into dt is nothing but V0. Therefore V0 is equal to minus 1 by R1 into CF integration of V into dt, and where in this equation 1 by RF R1 into CF is constant, and this equation shows that output voltage is the integration of the input voltage. The term indicates, negative term indicates the gain, negative term indicates that the gain of the amplifier, minus 1 by R1 into CF is the gain of the amplifier. So next application is that the differentiator. So in this application you are observing that the feedback element is resistor and the input element is capacitor. In the differentiator circuit, the output voltage is differentiation of the input voltage. The figure shows the differentiator circuits using the operation amplifier. So again, using the virtual ground concept, the potential node B is equal to 0. Then because of the virtual ground concept, potential node A is also equal to 0. So then find out the current which is flowing through the capacitor and also the resistor. So VA is equal to VB is equal to 0. Fine. Next, the current flowing through this capacitor is nothing but I is equal to C1 into dV in minus VA by dt. Since VA is equal to 0, we can write I1 is equal to C1 into dV in by dt. Similarly, IF is equal to VA minus V0 by RF. Then VA is equal to 0. Then 0 minus V0 by RF. IF is equal to minus V0 by RF. Then since Opamp input current is 0, I1 passes through RF as IF. That is I1 is equal to IF. So I1 we evaluated here has C1 dV in by dt, and IF obtained here as minus V0 by RF. We equate these two currents, then finally we can write V0 is equal to minus RFC, RF into C1 into dV in by dt, where this shows that output is the differentiation of the input voltage, and the term minus RF into C1 is the gain of the amplifier. Next is comparator. So the Opamp can also be used as a comparator. This is the non-inverting applications of the operation amplifier, non-linear applications of operation amplifier. So comparator is a device where the Opamp which compares the two input signals, or the device which compares the input voltages applied at the inverting and the non-inverting terminal of the Opamp. Sometimes the input voltage applied at the inverting terminal, which is comparing with the reference voltage also. If the Vin which is greater than V reference, means output voltage is plus VCC, or if Vin is less than V reference, then Vout is equal to minus VCC. You are observing the saturation voltages plus VCC and minus VCC. Next we see the operation of the comparator. Opamp comparator compares one analog voltage level with analog voltage level. That voltage level may be preset reference voltage or V reference, and produces an output signal based on this voltage comparison. In other words, Opamp voltage comparator compares the magnitude of the two voltage inputs and determines which is larger of the two. With the reference to the Opamp comparator circuit above, let's first assume that Vin is less than the DC voltage level at V reference. That is, Vin is less than V reference. So as I told you, if Vin less than V reference, then what is that? One of the voltage which is saturated there, as the non-inverting terminal, non-inverting input of the comparator is less than the inverting input, the output will be low, and at the negative supply voltage minus VCC is resulting in negative saturation of the output. And if we now increase the input voltage Vin so that its value is greater than the reference voltage V reference on the inverting input, then output voltage rapidly switches I towards the positive supply voltage. That results in plus VCC in a positive saturation of the output. If you reduce again the input voltage Vin, so it's slightly less than the reference voltage, the Opamp switches back to its negative saturation voltage, acting as a threshold detector. So this is about the comparator. Comparator is a device which compares the voltage applied at the inverting terminal, one terminal, with the voltage applied at the other terminal. That one of the voltage will be the supply voltage, another voltage will be the reference voltage or free reference voltage. So that's all about the operation amplifiers and applications. Dear students, kindly study this application operation amplifier, which are very important for examination point of view. This the module is a very simple module, very simplest module. So only three the videos I am shooting here. One is the characteristics, then definitions of various parameters of the operation amplifier, and what is the basic block diagram of the operation amplifier. And in the second video, I explained about the three applications, like how Opamp can be used as an inverting amplifier, how Opamp can be used as an non-inverting amplifier, and how Opamp can be used as an inverting adder. And in the last video, I explained about how Opamp can be used as a voltage follower, then how Opamp can be used as an integrator, and how Opamp can be used as a differentiator, and also how Opamp can be used as a comparator. So thank you for watching the video.